Well, chemists, welcome to TP's Chemistry Cuts. In this clip, we introduce the equilibrium constant, Kc, which is used to describe the concentration of products relative to reactants when a system is at equilibrium. We then use a balanced chemical equation to derive an expression for Kc and go on to see how the value of Kc gives an indication of the position of equilibrium.
Now, the first thing to say, and this is very important, do not assume that all reversible reactions give the same proportion of reactants to products. That's not true at all. Depending on what reaction you've got, some systems that reach equilibrium, it's mostly reactants still, and only a very small amount of product. But if you take that product away, the reactants will react together to form and put some more back until it reaches equilibrium again. Okay? Other reactions, it goes almost the other way, where you've always got entirely products for a small amount of reactants, whereas some reactions are somewhere in between. So it's really important we have some way of giving an indication of where we are in that terms of that proportion of reactants to products or products to reactions. So if you've got this sort of like weighing scale pointer, where does it point? Does it point towards the reactants or to the products, or is it somewhere in between? And that's where the equilibrium constant comes in. It's just a value that gives you a feeling for how much in terms of concentration of products you've got compared to your reactants. Okay? Okay, so that's basically what Kc is. It's telling you how much of the products you've got relative to reactants. Remember, this is always going to be in terms of concentrations. Okay. So let's look at a general reaction. Not going to look at a particular one just yet. We'll come back to a particular one. We need some way of actually working out this Kc. Okay, so for a very general reaction, so we've got A plus B. I'll leave all the states off, it doesn't matter for the moment. C plus D. Okay. Then for that very simple reaction there, Kc is equal to the concentration of C. I'll just come back to that in a minute. The square brackets are very important. This is something new. Okay. So if you put square brackets around something, that means you're specifically referring to its concentration. So, okay. Notice it's multiplying and dividing only. Do not put pluses in there because there's a plus here. Don't put a plus there. It's always times. Now, there's one more thing to bear in mind. I've conveniently assumed it's one of these reacts with one of these, giving one of those and one of those. What happens if you've got multiples? Why don't we have a look at an example and we can work it through? Okay. We've got this problem here. We've got a 3 there and a 2 there. What do we do about it? Do we put a 2 and a 3 in those positions? The answer is no. Let's work it through. If we were to take that, and don't ever do this, this is just to show you how it works. This is the equivalent of saying one of those reacts with 3 of those, doesn't it? So why don't we write it out in full? So N2 plus H2 plus H2 plus H2. Yeah? So all I've done is just expanded it out. I mean, you wouldn't want to do this in reality. And that means we've got 2 of these. Yeah? Hopefully I haven't confused anybody by drawing it out there. I'm just basically putting it in very longhand form. Now we can take that and apply this. Yeah? So for this one, Kc is equal to the concentration of that times the concentration of that again, divided by the concentration of N2 times H2 times H2 times H2, all three of them. I can simplify that, can't I? What can I put on top? Concentration of NH3 squared. And then we've got N2 times the concentration of H2 cubed. So in other words, you don't put the number down here, you put it as a power up here. So whatever the number is there, it's the power you put here. Yeah? So I'll just do a little sort of a highlighter. Like that. Okay. So do not use pluses and do not put the numbers in front. They're always the power. Okay, so what's this one? Concentration of HCl squared divided by H2 times that. So quickly put that, shall we? That's concentration of HCl squared divided by concentration of H2 times Cl2. Okay. When you're asked to give an expression's got a subject to it. Bit of maths there for you. So you should write Kc equals. These days, they sort of do everything for you because they'll give you a little box and they'll put Kc equals in the actual exam. Because it used to be, they didn't. This one, quickly.
It's O3 squared O2 squared O2.
Q, and this one. Okay, so let's remind ourselves using the reaction that we had at the end of the last lesson, the Haber process one, where we make ammonia, how we calculate the equilibrium constant and remind ourselves of what it means, and then we can start using the number itself to show what it actually means. Okay, so we'll look at the maths of it. It's very simple math, and it's very easy to interpret. When we see a value of it, what that value is telling us, because that's the first step. Now it's given the symbol Kc. Now you'll see that, particularly when you go on to level 3, that there'll be different little letters down here with K associated with it. Okay, and this is because they are very specialist things. Here we're just looking at any reaction involving reversible reaction. Then this equilibrium constant applies to that particular type of event. It's not specific. So if we look at the Haber process, this is where we take nitrogen gas and react it with hydrogen gas to make ammonia. And don't forget to use the reversible arrow. Always must be there if we're talking about equilibrium. You must show it's a reversible reaction. And then for this reaction, then Kc is the ratio of, or the product concentration to the reactant concentrations. And we represent concentration using these square brackets. Now, this is a great reaction because there's extra bits that we have to allow for. The fact we've got a 2 here means that we have to square this. Everything is either multiplied or divided. Okay, no pluses. Note this number shouldn't be at the front. It should be a power. Okay, so we've got nitrogen and then H2 cubed. Okay, so this is basically a number which is telling us something about the proportion of concentration of products to reactants. Okay, so we're going to unpack that a bit and look at what the value of Kc, if we get a number, what does that number tell us about that proportion? Okay, so let's write down first of all what this is telling us. Now the last part of that statement is actually very important. When we're looking at Kc, we're assuming the system has been reacting away and is then at equilibrium. In other words, there's no change in the relative concentrations of products and reactants. The reaction started and then it looks like it stopped, so we're at equilibrium. So Kc only applies when the system is at equilibrium. Okay? And it tells us the relative concentration, or the concentration of the products, in this case ammonia, relative to the reactants. Okay? So we're going to unpack that, as I said, and see what the value tells us. So let's do a little bit of maths, remind ourselves, that is a fraction. Okay? So when we're talking about fractions, we've got the top bit and the bottom bit. What's the top bit called? Let's remind ourselves of what the top bit's called and what the bottom bit's. What's the top bit called of a fraction? The numerator. What about the bottom bit? Denominator. So, what we are doing is we're looking at the size, relative size of denominator and numerators when we look at a number. Okay? So, if we consider the situation where Kc is a very large number, okay, so we've got a large number, what does that tell you about the size of the numerator in the fraction compared to the denominator? If it's a large number, much greater. It's telling us we've got a large numerator but a small denominator. In other words, it's telling us we have a high concentration of products, because this is products, relative to the reactants. In other words, equilibrium lies well over to the products. We've got more products, much higher concentration of products than we've got reactants. So that's if Kc is a large value, large number. Okay? We'll come to what we mean by a large number. What is a large number in terms of this in a bit. Okay? What about when Kc is a very small number? Very small number. Then it's the reverse, isn't it? It's telling us we've got a very large denominator, but a small, relative to the denominator, a small numerator. In other words, the concentration of products is high, whereas the reactants is high, but the products is low. So the concentration, always about the concentrations. High concentration, low concentration. In other words, when it reaches equilibrium, it's mostly that side. So we say it favours the reactants. It's over towards the reactant. So it's a reactant-favoured equilibrium. In the case where it's a large number, where we've got high concentrations of products, because it's a large number, big numerator, but small concentrations of reactants, small denominator, then it's telling us we're way over this way. This is what we call a product-favoured equilibrium. So large number, product-favoured, small number, reactant-favoured. And then anything in between, intermediate, then it's telling us you've got significant quantities of both reactants and products. So let's write that down. What we're focusing on then, and I really must emphasise this, is the value of Kc, what it's telling us. What type of equilibrium do we have? Do we have mostly reactants? Do we have mostly products? Or do we have something in between? And we can tell that by looking at that number. Okay? So let's write that down. So before I write that, actually, why don't we put what the numerator and the denominator relate to? So that's products. Okay, so we might brackets. So that's a simple way of putting it. A large number means a large numerator, small denominator. In other words, and this is the important thing, I'm going to put 2. What does that mean? Much bigger. Not just greater than, but much greater than. Let's do it. If you put 2 up them, it means much greater. So if you've got a high concentration of products and a low concentration of reactants, that's telling us that equilibrium favours the products, or it's a product-favoured equilibrium, either way around. And that's the expression we use, okay? Either a product-favoured equilibrium or equilibrium favours the products. Now when Kc is an enormous number, okay, that's telling us that the concentration of reactants has gone through the floor and the products has gone through the roof. In other words, you've basically gone to completion. So when you talk about a reaction going to completion, it means you've got no significant reactants left, they're all products. So if you get something like 10 to the power of 12 Kc, it's telling us you've basically completely reacted away all your reactants. Okay, so that's what we call has gone to completion. So here, it means that we haven't gone to completion because it's not huge, still large, but there's still some significant amount of products there, only in small concentrations, but it's enough to contaminate something maybe, so it's still there. Okay, to a point where we need to consider it. But our equilibrium is very much favouring our products. So this is a product-favoured equilibrium. Okay. One thing I haven't said, by the way, is that, and I need to emphasise this, any form of equilibrium constant does not have any units associated with it. So don't put any units, okay? None of them do, even the specialist ones. But Kc most definitely do not quote any units, because it's units. Okay, so when it's very small, you'll notice no units there. It's very small. So that's the other extreme. In a very small number means you've got a high denominator this time. In other words, the concentration of reactants is high, but a small numerator, So the concentration of products is low. So in other words, the equilibrium is lying way over towards the reactants. So reactant favoured equilibrium. So a reactant favoured equilibrium means you've got mostly or more higher concentration of reactants compared to the products. So it's not favouring either. Well, it depends. Slightly favouring, whatever that means. Okay. Now, although I'm giving you some values here, it's not sort of an abrupt cut-off. It's very difficult to say when something becomes suddenly very much a reactant-favoured equilibrium and which one is only slightly favoured. It's more continuous. But the idea is to give a general feel. Look to see whether you think that's a big number there. Is it a tiny number? Or is it somewhere around sort of something like 100, and you're thinking, well, you've got slightly higher concentration of products relative to the reactants, but you can have significant concentrations of reactants there because you're not out of reach with a very large number. Okay? Very useful way when you're doing discussions, okay, is rather than writing it all out in full. You notice there now I'm starting to use reactant concentration and product concentration. So when you want to use Kc in a generalised way, just put Kc equals the concentration of products divided by the concentration of reactants. And then when you start discussing, you can say, well, the products is going down and the reactants is going up, so Kc is going up. So it's easier to do it in that way. And there will be a situation where you will do something like that. Okay, and I'll put that in a red box because that's important. Get your highlighters out. That's what Kc is all about. That tells you it's the concentration of products relative to the reactants. So in a generalised way, when you're discussing it, that's the best expression to use. Okay, so when you're talking about the value of Kc, always think in terms of numerators and denominators. Products, reactants.